A very pleasant morning to everyone gathered here. Learning gives creativity, creativity leads to thinking, thinking provides knowledge, and knowledge makes us shine. With great happiness and heartfelt respect, I welcome our respected principal, Honorable Chief Guest, beloved faculty members, and dear students to this wonderful program organized by the PG Department of Computer Science, Sri Chandra Prabhu Jain College. I am Ms. A. Nirmala, Assistant Professor, Department of Computer Science, and it gives me immense joy to be the master of ceremony for today's event. Every successful event begins with warm greetings and positive thoughts. Now I would like to present the welcome address. It's our privilege to welcome our esteemed chief guest, Dr. K.Rajasekaran from D.B.Jain College, who is here to share his valuable knowledge through today's expert talk. I also extend my heartfelt welcome to our respected principal, Dr. N. Sujata ma'am, our HOD, Mr. K. Kumresan sir, faculty members, and dear students. I hope today's session will be informative, inspiring, and beneficial to everyone. Once again, I welcome you all. A meaningful introduction creates the path for an inspiring session. Now I request Mr. K. Kumaresan, Head of the Department of Computer Science, to introduce our esteemed chief guest. Welcome, sir.
Good morning, everyone. It's my privilege to introduce today's chief guest, Dr. K. Rajasekaran. Dr. K. Rajasekaran is currently serving as an associate professor in the PG department and computer science at D.B.Jain College. He has more than 20 years of teaching experience in the field of computer science and information technology. He completed his PhD in computer science from Bardiyar University and has guided more than 1,000 MCS students and several MPhil scholars. He has published more than 50 research papers in national and international journal and conference. Dr. Rajasekaran has actively organized international conference, workshop, faculty development programs, and academic programs. He also served as ERP coordinator, UMIS nodal officer, scholarship nodal officer, and contribute significantly to NAC, AQAR, AICTE, and autonomous extensions activities. His dedication to education and academic excellence earned him the Best HOD Award in 2024 and the Best Professor Award in 2025. We are greatly honored to have such as eminent academician with us today. On behalf of our institution, I extended a warm welcome to our respected chief guest. Thank you.
Thank you, sir. It's always a privilege to listen to experienced minds who inspire young hearts. It's now time for the expert talk by our esteemed chief guest, Dr. K. Rajshekharan, Associate Professor, Department of Computer Science, D.B. Jain College. Welcome, sir.
Thank you, Ma. Thank you. Sir, respected Kumar Jain, sir, Secretary, Sri Chandrababu Jain College, respected Dr. Sujata ma'am, Principal, Sri Chandrababu Jain College, Professor Kumreshan, HOD, PG Department of Computer Science, faculty members from various departments, students, and participants from various colleges. It's a good morning to one and all. First, I would like to express my sincere thanks to the management for inviting me as the resource person for this webinar on blockchain technology with the IoT. And I also thank Mr. Kumresan for introduction about me. And this webinar, that is blockchain meets IoT, it explores how blockchain and Internet of Things technologies work together to create secure, transparent and intelligent systems for industries and smart environments. So this webinar explores how blockchain and Internet of Things technologies work together to create secure, transparent, and intelligent systems for industries and smart environment. Then the today's agenda of this webinar. So first we discuss about introduction to Internet of Things, that is IoT. Then we discuss about the blockchain technology. The next we discuss about why blockchain with IoT. What is the need for blockchain with IoT? The next we discuss about the topic IoT architecture challenges. What are the challenges on the IoT architectures? Then next we discuss about blockchain integration architecture. The next, real world applications. So there are various applications in the real world. We discuss about the applications. Next we discuss about the benefits and opportunities of the blockchain with IoT. Then the integration challenges. Next we discuss about the integration challenges and limitations. The next we discuss about the future trends, and finally question answer session. The introduction to IoT. So IoT refers interconnected physical devices embedded with the sensors, software, and communication technologies that collect and exchange real-time data over networks. So the introduction about the IoT. So the introduction that is IoT refers to interconnect physical devices embedded with the sensors, software, and communication technologies that collect and exchange real-time data over networks. Then the applications of IoT, where we discuss about some of the applications of IoT architectures. The first one is smart agriculture. So the smart agriculture is the irrigation schedules, automates irrigation schedules, monitor soil conditions, and analysis crop health using real-time sensor readings. The first application is smart agriculture. It automates irrigation schedules, monitors soil conditions, and analyzes crop health using real-time sensor readings. The next application is asset tracking. So the asset tracking is monitors the movement of vehicles, shipments, and equipment using GPS, telemetry, and beacon signals. So the asset tracking, it monitors the movement of vehicles, shipments, and the equipment using GPS, telemetry, and the beacon signals. The next application is smart grids. It it balances power distribution, forecast consumption patterns, and reduce transmission losses dynamically. So the smart grids, it focuses on balance power distributions. It balances power distribution, forecast consumption patterns, and reduces transmission losses dynamically. The next one is home automation, that is smart home. It controls lighting, door locks, applications, and the climate settings based on the user behavior patterns. The home applications are smart home application. It controls lighting, door locks, appliances, and the climate settings based on user patterns. Then next application is industrial automation. It predicts machinery faults, schedules maintenance, and improve production accuracy in factories. So the industrial automation, it predicts machinery fault, schedules machinery maintenance, and improves production accuracy in the factories. See, these are some applications of IoT. So the major application is smart agriculture, then the asset tracking, smart grids, home automation or smart home, industrial automation. These are the some applications of IoT. The next one is IoT ecosystem. The IoT ecosystem consists of sensors, gateways, cloud platforms, analytic engines, and end user applications working together for automation and monitoring. So the IoT ecosystem it consists of sensors, gateways, cloud platforms, analytics engines, and end user applications working together for automation and monitoring. This is the IoT ecosystem. The next one is IoT architecture. Next, we discuss about the architecture of Internet of Things. A typical IoT architecture includes sensing devices, communication networks, cloud storage, analytics layers, and user-facing applications. A typical IoT architecture includes sensing devices, communication networks, cloud storage, analytics layers, and user-facing applications. Then the architecture diagram of IoT. This is the typical IoT architecture is organized into multiple layers, each performing specific functions. IoT architecture consists of multiple interconnected layers. This is the diagram shows the typical IoT architecture. It is organized into multiple layers, each performing specific functions. IoT architecture consists of multiple interconnected layers. The bottom of the layer is device or sensing layer. The bottom of the layer is device or sensing layer. The next layer is network layer. The next one is data processing layer. And the topmost layer is application layers. There are 4 layers. The bottom of layer is device layer. The next one is network layer. The next one is data processing layer. And the topmost one is application layer. First, we discuss about the device layer. Device layer means the sensing layer. This device layer is bottommost layer responsible for detecting physical conditions from environment. This layer, that is this layer is device or sensing layer. This is a bottommost layer responsible for detecting physical conditions from the environment. Next, the functions of device layer. It collects raw data such as temperature, humidity, motion, and sound or pressure. It collects is a function of the device layer as follows. The first one is it collects raw data such as temperature, humidity, motion, sound, or pressure. The next one is senses changes in the surroundings through embedded components. The next function is senses changes is monitor senses changes in the surroundings through embedded components. Then next, it initiate actions using actuators when required. It initiate actions using actuators when required. These are the functions of device layer. That's collect raw data such as temperature, humidity, motion, sound or pressure, senses changes in the surroundings through embedded components, initiate actions using actuators when required. Then the components of the device layer. So there are various components of device layer. There are sensors like humidity, gas, infrared, and ultrasonic. The sensor la pathina humidity, gas, infrared, and uh, ultrasonic. The next actuators components like motor, switches, valves, and etc. So it's motor, switches, valves, and etc. Then the components of microcontrollers, components are the microcontrollers and the RFD tags. Then the communication, it transfers censored data to the network layer via either wired or wireless network. It transfers censored data to the network layer, either wired or wired links. These are the functions of sensing or device layer. So this is the bottom most layer responsible for detecting physical conditions from the environment. The next layer is network or transport layer. The second layer is network or transport layer. This layer provides connectivity and communication between IoT devices and cloud systems. This network layer provides connectivity and communication between IoT devices and cloud systems. Then the functions of network layer, it transmits collected sensor data to processing platforms securely. So it transmits collected sensor data to the processing platform securely. The next function is supports device to device and device to server communication. It supports either device to device or device to server communication. Then the network layer handles addressing, routing, and data forwarding. It handles addressing, routing, and data forwarding. These are the functions of network layer. It transmits collected sensor data to processing platform securely. Then it supports device to device or device to server communication, and it handles addressing, routing, and data forwarding. The next one is technologies. The technologies are Wi-Fi. The technologies are Wi-Fi, Bluetooth, Zigbee, LoRaWAN, Ethernet, and satellite networks, supporting devices, and router switches. These are the technologies used in the network or transport layer. There are Wi-Fi, Bluetooth, Zigbee, LoRaWAN, Ethernet, and satellite networks, supporting devices, and routers and switches. So these are the layer of, that is the network and transport layer. This layer provides connectivity and communication between IoT devices and a cloud system. Next, we discuss about the third layer, that is data processing layer. The next one is, third one is data processing layer. This layer provides connectivity and communication between IoT device and cloud system. Sorry. This layer analyzes, filters, and interprets data received from network devices. So data processing layer, this layer analyzes, filters, and interprets data received from the network devices. Then the functions of data processing layer, it cleans and formats raw sensor data for meaningful insights. It cleans and formats raw sensor data for meaningful insights. And it applies analytics to detect patterns or abnormalities. It applies analytics to detect patterns or abnormalities. Then it stores data for historical analysis or reporting, and it stores data for historical analysis and reporting. These are the functions of data processing layer. The next one is the components of the data processing layer. There are various components. The first one is IoT cloud platforms. IoT cloud platforms, then data lakes and warehouses, then stream processing and machine learning engines. So IoT cloud platforms, data lakes and warehouses, stream processing and machine learning engines. So this layer is That is the data processing layer analyzes, filters, and interprets data received from network devices. Then next, what is the output of the data processing layer? It predictive alerts and reports. It predictive alerts and reports. It anomaly detection signals and decision rules for automation. These are the outputs of data processing layer. It predictive alerts and reports, anomaly detection signals, and decision rules for automation. The next one layer is the fourth one is the topmost layer is application layer. Next we discuss about the application layer. So there are four layers. The first one is device layer. Next one is data. Sorry. Next one is network layer. Third one is data processing layer. The last one is application layer. So the application layer, this is the most topmost layer, interacts directly with the end users and the business system. So it is the topmost layer. It interacts directly with the users and the business systems. Then the functions of application layer, it provides interface to monitor, control IoT devices remotely. It provides interfaces to monitor and control IoT devices remotely. And it displays virtual analytics through dashboards and chart. It displays virtual analytics through dashboards and chart. And it triggers automated actions based on proceeded insights. It triggers automated actions based on proceeded insights. The next one is the components of the application layer. So there are various components, that is mobile application, web dashboards and portals, visualization and alerting tools. So mobile applications, web dashboards and portals, visualization and alerting tools. These are the components of the application layer. The next one is capabilities. The capabilities of application layers are remote device management. It's a remote device management, real-time condition monitoring. It is a real-time condition monitoring and the integration with the enterprise application and integrates with enterprise applications. These are the capabilities of application layer. So basically, so there are four layers. The first one is device layer. This is the bottommost layer responsible for detecting physical conditions from the environment, and the communication is a transfer sensor data to the network layer via wired or wireless links. The second one is network or transport layer. This layer provides connectivity and communication between IoT devices and the cloud system. And the third one is data processing layer. This layer analyzes, filters, and interprets data received from network devices. And the fourth one is application layer. This is the topmost layer, interacts directly with end users and business systems. And the capabilities are remote device management, real-time condition monitoring, and integration with enterprise applications. So these are the IoT architecture. Next we move on. Challenges in IoT. Challenges in IoT technology. IoT systems face major challenges such as cybersecurity threats, lack of interoperability, device management complexity, and data privacy concerns. So the IoT system face major challenges such as cybersecurity threats, lack of interoperability, device management complexity, and data privacy concerns. Next, we will discuss about some challenges in the IoT. Some of the major challenges in the IoT. The first one is security vulnerabilities. And the second one is high initial cost. The next one is compatibility challenges. The next one is network dependency and the complex maintenance. These are the some challenges of IoT. The first one, security vulnerabilities. Its connected devices are susceptible to cyber attacks, unauthorized access, and data breaches due to weak security layers. Then the high initial cost. It is implementing sensors, gateways, and the communication infrastructure requires significant upfront investment. So the high initial cost. So that is high investment. It is implementing sensors, gateways, and the communication infrastructure requires significant upfront investment. There is more investment in the IoT technology. Then the compatibility challenges. Different vendor standards and communication protocols create difficulties in integrating heterogeneous system. So it is different vendor standards and the communication protocols create difficulties in integrating heterogeneous system. The next one is network dependency. Connectivity issues can interrupt data follow and distribute real-time operation across remote deployment. So network dependency, connectivity issues can interrupt data flow and disrupt real-time operations across remote deployments. Then the complex maintenance, large-scale IoT deployments require continuous monitoring, regular updates, and specialized management tools. Then why centralized platforms became bottleneck? Centralized systems uh, process data, execute rules, and store information in one core location. So why the centralized platforms became bottlenecks? So centralized system process data, execute rules, and store information in one core location. This architecture creates three major type of bottlenecks. There are network latency and bandwidth. The first one is network latency and bandwidth. The next one is computational strain and the single point failure. So there are three major bottlenecks, that's network latency and bandwidth, computational strain, and single point of failure. The single point of failure, if the central platform experiences on outage, configuration error, or physical failure, the entire IoT network goes offline. Individual nodes cannot function independently, halting operations across the board. So the single point failure means in the central, if the central platform experience an outage, a configuration error or physical failure, the entire IoT network goes offline. Individual nodes cannot function independently, halting operations across the board. Then why centralized platforms are prime target for hackers? So consolidating massive amounts of data and controls into one accessible location transforms these platforms into highly vulnerable target for cyber criminals. These are the honeypot effect, cascading control, massive botnet requirement, and the API explanation. The next we discuss about blockchain technology. That is introduction to blockchain technology. So blockchain is a decentralized distributed ledger technology that stores transactions securely across multiple nodes without requiring a central authority. So the blockchain technology is a decentralized distributed ledger technology that stores transactions securely across multiple nodes without requiring a central authority. The key features of blockchain technologies are transparency, security, traceability, decentralization, and smart contracts. So these are the key features of blockchain technology. The key features are transparency, security, traceability, decentralization, and smart contracts. Next one is the blockchain architecture. The blockchain architecture includes distributed nodes, cryptographic hashing, conscious algorithms, smart contracts, and immutable ledgers. The blockchain architecture, it includes distributed nodes, cryptographic hashing, conscious algorithms, smart contracts, and immutable ledgers. Then the blockchain architecture creates a decentralized ledger system that uses cryptography to ensure the immutability and integrity of digital information. The blockchain architecture creates a decentralized ledger system that uses cryptography to ensure the immutability and the integrity of digital information. And it is the its core, it is the continuously growing list of records called blocks linked together using cryptography to form a chain. To link it together using cryptography, and it is to form a chain. So it's an architecture diagram. Each block in a chain are structured by blockchain architecture. Each block in a chain as structured by blockchain architecture. It contains a batch of verified transaction added to the blockchain in sequential order. It contains a batch of verified transaction added to the blockchain in sequential order, creating a permanent and a transparent record of all transactions on the network. The decentralized nature of the blockchain architecture means there is no central authority on or a single point of failure, making it highly secure and resistant to fraud and hacking. The decentralized nature of the blockchain architecture means there is no central authority and there is no single point of failure, then making it highly secure and resistant to fraud and hacking. The next one, how blockchain works. Blockchain validates transactions through conscious mechanisms, groups them into blocks, and links them cryptographically to ensure tamper residence. Blockchain validates transactions through conscious mechanisms, groups them into blocks, and links them cryptographically to ensure tamper residence. The next one is smart contracts. The smart contracts are self-executing digital agreements that automate workflows and a transaction when predefined conditions are met. So in the smart contracts, it's a self-executing digital agreement. It's a self-executing digital agreement that automate workflows and a transaction when predefined conditions are met. Then how it works? How the smart contracts are work? There are three things: code is law, automation, and immutability. The first one is code is law. The terms of the agreement are written directly into lines of code and deployed to a decentralized blockchain network. Code is law. The terms of agreement are written directly into lines of code and deployed to a decentralized blockchain network. The next one is automation. When specific conditions are verified, the network automatically executes the actions such as transferring funds, unlocking asset, or updating a record. The automation, when specific conditions are verified, the network automatically executes the action such as transforming funds, unlocking assets, and updating records. Then immutability. Once a smart contract is deployed, its instruction cannot be altered or deleted. Once a smart contract is deployed, its instructions cannot be altered or deleted, ensuring total transparency and trust. So these are the small contracts. The next one is why we need combine blockchain and IoT. What's the need? The combining blockchain with IoT creates trusted ecosystems where devices can communicate securely without relying on centralized intermediaries. Why combine blockchain and IoT? What's the need? The combining blockchain and IoT creates trusted ecosystems where devices can communicate securely without relying on centralized intermediaries. Next one is the benefit of blockchain in IoT. Benefits of blockchain in IoT. Blockchain improves IoT through enhanced transparency, secure automation, decentralized trust, auditability, and operational resilience. So blockchain improves IoT through enhanced transparency, secure automation, decentralized trust, auditability, and operational resilience. The integration benefits are some of the major benefits are secure device communication, tamper-proof data storage, decentralized trust management, automated machine-to-machine transactions, enhanced transparency, and improved scalability through distributed networks. The major benefits are secure device communication, tamper-proof data storage, decentralized trust management, automated machine-to-machine transaction, enhanced transparency, and improved scalability through distributed networks. The security improvements, blockchain. The blockchain strengthens IoT security by protecting data from tampering, eliminating single points of failure, and improving cyber resilience. Blockchain strengthens IoT security by protecting data from tampering, eliminating single points of failure, and improving cyber resilience. Then blockchain enhances IoT security by device identity management, data encryption and integrity, secure framework updates, decentralized automation, and preventing unauthorized access. So blockchain enhances IoT security by device identity management, data encryption and integrity, secure firmware updates, decentralized authentication, and preventing unauthorized access. The next one is data integrity. So immutable blockchain records guarantee data integrity by ensuring IoT data cannot be altered after validation and storage. The underlying mechanisms that guarantees this level of data integrity include cryptographic hashing, decentralized distributed ledger, and the census mechanisms. Cryptographic hashing, decentralized distributed ledger, and conscious mechanisms. The cryptographic hashing means every data block contains a unique hash and the hash of processing block. If data is altered, its hash changes completely, breaking the chain and exposing the tampering. The next one is decentralized distributed ledger. It copies of ledger are maintained across the multiple nodes in the network. To successfully fastly to entry, an attacker would need to alter the data across the majority of these nodes simultaneously, which is virtually impossible. Then conscious mechanisms. Before IoT data is written to a block, it is verified by the network nodes through a conscious protocol. This ensures only validated and trusted information is recorded. The next one is decentralized IoT networks. Decentralized IoT networks enable peer-to-peer communication between devices, reducing dependence on centralized cloud infrastructure. Next one is device authentication. Device authentication is a blockchain-based identities allow IoT device to authenticate securely, preventing unauthorized access and device pooling attacks. The next one is supply chain use case. In supply chains, blockchain and IoT sensors improve tracking, traceability, temperature monitoring, and counterfeit prevention. The benefits of the supply chain are improved visibility, faster auditing, and reduced counterfeit products. In supply chains, blockchain and IoT sensors improve tracking, traceability, temperature monitoring, and counterfeit prevention. Then the benefits are improved visibility, faster auditing, and reduced counterfeit products. The next one is smart cities use case. Small cities use blockchain IoT for intelligent traffic management, waste monitoring, smart parking, public safety, and energy optimization. Smart cities use blockchain and IoT for intelligent traffic management, waste monitoring, smart parking, public safety, and energy optimization. IoT can be used in many ways to make cities more efficient, ranging from managing the traffic, controlling air pollution, handling waste management, creating smart buildings, planning for natural disasters, and etc. These are the use case of smart cities. So the main thing is it maintain the traffic management, waste controlling, smart parking, public safety, and energy optimizations. The next one is healthcare IoT use case. Healthcare IoT systems use blockchain for secure patient monitoring, medical record management, and privacy preventing data sharing. The healthcare IoT systems use blockchain for secure patient monitoring, medical record management, and privacy preserving data sharing. The benefits of the healthcare IoT, so it's improved patient privacy. Then real-time healthcare monitoring and data transparency. These are the benefits of the healthcare IoT. So the first one is improved patient privacy, real-time healthcare monitoring, and data transparency. The next one is Industrial IoT, IIoT. The industrial IoT applications include predictive maintenance, automated manufacturing, asset tracking, and real-time operational analytics. The industrial IoT applications include predictive maintenance, automated manufacturing, asset tracking, and real-time operational analytics. The benefits of the industrial IoTs are it is reduce the downtime and better operational efficiency and enhanced data security. The benefits of the industrial IoTs are it reduces the downtime and it's better operational efficiency and it's enhanced data security. These are the benefits of IIoT, industrial IoT. The next one is energy and smart grids. Smart grids leverage blockchain for secure energy trading, decentralized energy management, and transparent billing system. Smart grids leverage blockchain for secure energy trading, decentralized energy management, and transparent billing systems. The next one is edge computing and blockchain. The edge computing process IoT data closer to device before storing validated transaction on blockchain networks, reducing latency. So the edge computing process IoT data closer to devices before storing validated transaction on blockchain networks, reducing latency. Then why edge computing is needed? It reduces latency, faster processing, lower bandwidth usage, and real-time analytics. Then integration with the blockchain with secure edge transaction, local smart contract execution. So integration with the blockchain, it's secure edge transaction, local smart contract execution. The next one is AI, blockchain, and IoT. The convergence of AI, blockchain, and IoT enables autonomous decision making, predictive analytics, and intelligent decentralized system. The major advantages are stronger cyber security, enhanced trust, decentralized control, better transparency, reduced operational cost, and automated workflows. It is improved compliance and auditing. These are the major advantages. That is stronger cyber security, enhanced trust, decentralized control, better transparency, reduced operational cost, automated workflows, and improved compliance and auditing. Then the popular platforms are the popular platforms supporting blockchain and IoT include Ethereum, Hyperledger Fabric, IOTA, IBM Watson IoT, and AWS IoT services. These are the popular platforms of blockchain and IoT. The next one, challenges of integration. Integration challenges include scalability limitations, energy consumption, transaction latency, regulatory and uncertainty, and interoperability issues. So these are the major challenges of integration. One of the main challenges in the integrating blockchain with IoT is scalability of blockchain technology. The number of IoT devices is expected to grow rapidly in the coming years, and the blockchain networks may struggle to handle to sheer volume and transaction generated by these devices. To address these challenges, new conscious algorithms and block validation methods need to be deployed that handle a high volume of transaction efficiently. The another major challenge is interoperability, and another one is security issues. These are the challenges of integrations. Scalability solutions. Scalability solutions include layer 2 protocols, shading, light chains, lightweight conscious algorithms, and edge-based transaction processing. The future trends uh, include decentralized autonomous machines, machine-to-machine payments, digital twins, and AI-driven smart ecosystems. These are the emerging innovations. That is AI-powered IoT blockchain systems, Web3 and decentralized applications, 5G-enabled IoT ecosystems, digital twins, decentralized autonomous organization, and quantum resident blockchain security. These are the emerging trends. Now the case study: blockchain enabled cold coin monitoring uses IoT sensors to track food and medicine temperature in real time for compliances. The next one is key takeaways. Blockchain and IoT together deliver strongly security, trusted automation, improved transparency, and decentralized intelligence. So, blockchain and IoT together deliver stronger security, trusted automation, improved transparency, and decentralized intelligence. So, now I conclude my webinar. I am thanks all the participants for attending this webinar. That is uh, blockchain meets IoT. We welcome your question, discussions, and feedback regarding blockchain and IoT integration. Thank you for your patient waiting. Thank you all. Thank you all once again.
Thank you, sir, for your inspiring and valuable speech. Your words will surely enrich all of us. Gratitude is the sweetest form of respect. Now I request Ms. M. Mahalakshmi, Assistant Professor, Department of Computer Science, to deliver the vote of thanks.
Good morning to everyone present here. It is my proud privilege to propose a word of thanks for today's programming. First of all, I express my sincere gratitude to our respected chief guest, Dr. K.Rajasekaran from D.B.Jain College, for delivering such an informative and inspiring expert talk. Your valuable words and insights have truly enriched us, sir. It extends my heartfelt thanks to our respected Secretary of Sri Chandraprabhu Jain College for the continuous support and encouragement provided to organizing this program successfully. I extend my heartfelt thanks to our respected principal, Dr. N. Sujata, for the constant support and encouragement in making this program successful. I also thank our head of department faculty members and dear students for our enthusiastic participation and cooperation. My special thanks to the pro and technical staffs for the valuable support and coordination in organizing this program smoothly and successfully. Finally, I thank everyone who worked behind the scenes and contribution to the success of the event. Once again, thank you for all the gracious present. Have a wonderful day. Thank you.
Thank you,
Thank you,
everyone,
ma'am.
for your gracious presence and support. May this program, sir,
Okay, ma. Thank you, ma. Thank you all. Thank you for.
thank
Thank
you,
you very
sir.
much, sir.
Thank you, sir.
Thank you.
Thank
Thank
you,
you.
ma. Thank you.